If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started. I'm sure if you use internet, you must have definitely ordered food online. And what do you consider first when you're ordering food? Of course, the ratings of the restaurant. So this case study is about predicting the average ratings of a restaurant given certain features. It's a real-world data set which has some interesting attributes. So we'll go through this entire exercise one by one. This dataset has been obtained from Kaggle, and a link to the dataset will be provided to you in the description. Let's first start by importing the basic libraries like NumPy and Pandas, and then we read the dataset using Pandas read_csv method. The file is called zomato.csv. It would take some time to read this data because this is a relatively large file. And now that the data has been read, let's quickly start by checking its attributes. So we'll first check the shape of the data. It has about 51,000 rows and 17 features. And if you want to glance through the first few rows of the data, we can do a head. And you see this has a lot of features, like there is a URL, there is a link to the specific page that belongs to the restaurant. Then there is the address, there is the name of the restaurant, then a couple of other features related to the orders. For example, it's an online order or a takeaway. And did the guest book the table or place an order online only? This is the rating column, which is what we are intending to predict. And then we have the votes or likes for the restaurant. And then we have the contact details, location, restaurant type. These are categories. What are the dishes that people usually like at this specific place? What kind of cuisines does the restaurant offer? And approximate cost for 2 people. Plus, there is a column which is related to reviews. So this has a lot of free text in it, which of course would not be very useful for this case study because we are primarily focusing on the machine learning aspects, not necessarily on the natural language processing. Then we have a list kind of a feature for menu items. There are times when it is blank, but there are times when you have a long list. And then we have listed in type. So what category is the restaurant listed in and listed in what location? So listed in what location is about the restaurant, and the location here is about the delivery location. Now, we'll just do some general exploratory analysis, and then we will analyze these features one by one. So let me just show you the data types. So we have a mix of variables. Majority of them seem to be objects, and then we have integers as well. Let's check the features in the data. So this is a list of features. In a way, we just glance through these. Here is that list at one place. Now, we may want to first check how many unique categories does an object type variable contain. In order to do that, what we are doing is we are running a loop. We are saying for each column in the object type columns. So we are using this method called select_d types, where we are filtering those columns which are objects. Essentially, all the columns are objects except one. Then for each feature, we are printing the name of the column, and we are checking how many unique categories does it have. And we are printing a space after each output. Let's run this. So we can see that URL has 51,700 rows. That's unique for every single row. And address has 11,000 unique locations because there could be restaurants located at a specific place, a mall or something like that, and they have repetitions. Then we talk about unique categories. We have about 8,700 unique categories. Online order, book table are binaries. Then we have ratings, and we have 64 different types of ratings. Now, this is a value that we have to convert it to. Right now, Pandas is reading it as an object. Phone numbers, again, would not be a very useful predictor for predicting the rating. But if we talk about location, we have 93 locations, 93 categories of restaurants. And then we have dishes liked, about 5,200 dishes liked by individuals. Then we have 2,700 plus cuisines. So there are many categorical variables you can see, including reviews. Of course, reviews are supposed to be somewhat unique. So we have 22,500 odd values. Looks like some reviews could be common. And then we have menu items, about 9,000 entries here. We have the listed in type. So in what category is the restaurant listed? There's 7 such categories, and listed in city, we have 30. Let's now check the presence of missing values in the data using isNull.sum. And then we see that there are a number of features. Like, for example, the target column itself has missing values, phone number has missing values, location has missing values, restaurant type, dish liked, cuisines, and approximate cost also has missing values. Now, one thing that we need to be very clear about fundamentally is that we do all the missing value treatment only for the independent variables. We never do missing value imputation or treatment for the target column. We are supposed to predict that. So if any supervised problem that you're handling where the target column itself has missing values, you don't have a choice but to simply drop those rows. So these 7,775 rows will simply be dropped because this is the target, what we are interested in predicting. How do we drop that? We just do a drop NA, simplest method in pandas, where we mention based on which feature we are dropping, we're dropping it based on the feature called rate. For the other variables, the missing values that are there, we'll handle those. And we are doing this in place, so the change will take place at the source itself. We are printing the shape of the data frame before dropping the rows and after dropping the rows, and we are then checking the missing values just to ensure that we've kind of largely taken care of it. So if you see, we had 51,000 rows and we are left with around 44,000 rows after dropping the missing values for the target column. Notice that in the process, we've also dropped all the missing values for location, because those would have been appearing in the same row. When you drop an entire row, there could be other features also which have missing values, and looks like we've kind of dropped those as well. Let's check how many unique entries are there in rate, though that's supposed to be a numerical column, but since pandas is reading it like an object, let's just closely examine this feature. You see some ratings, and why this is seen as an object is because you see these entries as this by or forward slash and number 5, and this is written like a string. It's written in quotes, right? It also has some peculiar entries like new, and you know that in a particular column which has all the numbers, if even one single cell has anything other than a number or a decimal, that will be treated as an object by pandas. So is what is happening here. Because of this new, we'll further have problem, and there's also a hyphen here. So we'll have to take care of these forward slash 5s. And you notice some of these are with spaces, some of these are without spaces. So this 3.7 divided by 5 has a space in between. This 4.1 divided by 5 doesn't have a space. So these are some of the nuances we'll have to look at before we start our journey towards predictive modeling. Let's fix this. So we take the rate column, and wherever in the rate column we have this new, this pattern written or a hyphen, we'll replace it with a missing value to first recognize that this value is not present in the data. Then we are extracting only numbers from this specific column. So we are saying extract a pattern which is like a digit, one or more digits, followed by a decimal and one or more digits afterwards. So when we extract this pattern, we'll be left with entries like 4.5, 4.3, etc. because this is what we are capturing here, a digit followed by a decimal and another digit. So this forward slash thing would automatically be ignored. And then we are saying after we extract this, we still have to convert this to a number because pandas originally sees this as an object. We'll change that. However, in the process, if we encounter any place where we do not have a number, we are not able to extract the digits as is, then we would want to convert that to a NaN. So when you see what is this course doing here, it's supposed to convert anything which is not as per our expectation, anything which is not a number, to a NaN. That's what we will do by doing this. Let's just run this, and then we can check is na.sum or is null.sum and see that we have another 2,277 entries which have been coerced as errors due to this conversion. What we can do is we can simply drop these rows as well so that we have a proper column for rate available. So this has done it. And now if we check the missing values, a sum, we do not have any missing value in the data. Let's check for the unique entries now. And you see that all the appearances here are appropriate. We don't have NaNs and we don't have any string present here. This, if you want to check the data type for this also, we can run this and this says it's a float data type. Couple of other issues with features like approximate cost for 2. That's a pretty long name. When we'll be working on it, when we'll be typing it, it'll be a lot of effort. So to simplify that, we can always use a dot rename method, and we can do this for multiple columns in the form of a dictionary. This is the key, which is how the name currently appears. This is the value that we are changing it to. So we are converting it to a simple appearance, which is cost, and we can check the unique levels in cost now. The cost also has some unique entries. That's what we see. But even now, this cost would be not read as a number by pandas because this again is in the string format. You see these quotes here and you see these commas also here. So we are fixing this as well for the cost column. We are saying, let's replace the comma with a blank, doing regular expressions, a general pattern, convert it to a float. And whenever we encounter a missing value, we will replace it with a median cost. We are not replacing with the mean because there may be outliers present. They could be high-end restaurants. They could be very economical restaurants. So not to take a chance, we are replacing it with a median. And then we are checking how many missing values are there in this column. We have none. So for the cost column, again, we've taken care of the data type and we've taken care of the formatting issues. Now we'll be focusing on some feature engineering. Feature engineering is about deriving new features from the given information, right? So we know there are places like listed in city, and it has many entries. We saw it has about 30 odd entries. And then we can just quickly check how these unique entries are. So this is, if you see, a long list. Now, this is a categorical variable which has 30 entries, 30 unique categories. Think about this. If we want to do a one-hot encoding on this, would that be fair? Maybe not, because that will be too many columns. If we like to do any ordering here or do an ordinal encoding here, that will also not make sense because we can't really give ratings or rankings to the locations so easily, especially when the number is 30. All we can do is we can try to represent the same information in a different format. So we try to map these 30 places to different directions: north, east, west, south, and central, 5 levels. This is a dictionary that we have created. This data is for a specific city in India that's called Bangalore, and we've mapped it as per the directions. Finally, we are saying this column listed in city will contain this mapping that we have created above. And the map method here comes quite handy because we can directly pass this dictionary to the map method. It will change the mapping of the specific column. So we are doing that now. And then we can check the value counts. You can see now those 30 categories have been reduced to simple 5 categories: north, east, west, south, and central. South has the maximum entries, then east, then central, then west, and then north. Now we can do the same thing for location feature, but that was even more complex because it had about 93 entries. So let's just run this. Now we see 92 because when we dropped the rows earlier, maybe one of the categories got dropped. We have 92 entries now. And if we check, this again is a long list of these 92 localities. Again, if we check the way these names appear, these are of course more than the listed in city. This location refers to the delivery location. The listed in city refers to the location of the restaurant. Delivery location is the location of the customer, and listed in location is location of the restaurant. Let's see if we can do some mapping on that. It could be an assumption, but let's just try to explore that. Once again, we are doing nearly the same thing. We are creating a dictionary which has the mappings of these places. For each place, we have a mapping in terms of north, east, west, south, or central. And then pretty much like the previous column, except that there is more effort here. We are converting it to the location with 5 categories using the .map method. Let's run this, and this is the mapping that we got. So if this is the location of the restaurant and this is the location of the customer or the delivery location, we can try to see a relationship between these two. Is the order being placed from the same location where the restaurant is, or is the order being placed from a different location from another corner of the city? That could also have a bearing on the ratings, because if you live in one part of the city and you've ordered food from another part, it might take more time to deliver, and the temperature of the food and the freshness of the food could get affected. It's a hypothesis. We are just experimenting, and there's nothing wrong in doing that. Let's do a cross tab, and you'll see a 5x5 contingency table kind of an output. The diagonals represent those cases where the delivery location and the restaurant location was all in sync, and the off-diagonal elements represent those places where there was a mismatch. So based on these two things, we can derive a new feature. What we can do is we can say if the location and the listed city, which means location of the customer and the restaurant location, is same. We're checking that condition by using double equal to. If they're equal, then it will result into a true, and we'll convert it to an integer. So that will become a 1. And if not, then it will become a 0. It will be false, and we convert it to an integer, it will be a 0. So this will become a binary column for us that we can keep. So this is a feature-rich data. If you see, there are a lot of features, and there's a lot of scope of exploring the data from business perspective. Let's closely look at some more features like dish liked, reviews, and menu item. And let's check the unique entries in each of these. We kind of did that earlier, but we don't really remember those numbers. So good to check it again here. Let's see. So dish liked has 5,000 plus entries, reviews list has 21,000 plus reviews, and menu items has about 8,200 odd rows. Let's examine each of these one by one for specific value counts. So if you see why we are checking value counts, we don't want to see 5,000 values, of course, but we are trying to see, is there a pattern? Is it that out of these 5,000 entries, maybe 5 or 10 entries add up to about 80% of the occurrences, and then we can accordingly prioritize. But that doesn't seem to be the case here. Dish like, the most popular dish, if we talk about, exists for only 0.76% of the times. It's not even 1%. So you can't just keep on adding these because that will become a long list. So there's no way that we can simplify this column. Likewise, when we move to reviews list, if we check the value counts, these are 21,000 reviews. But again, this hints that we'll not be able to use this column. As such, this is more of a natural language processing stuff. which is a little beyond our scope at this stage. Now let's move to the menu items and see what we can do. So menu item seems to have about 73% such entries where this field is not even captured. It's a blank list. It doesn't have anything. And then you have long list of items. So these features that we talk about don't seem to be very, very meaningful. We may add them to the list of features we want to drop. Now let's go through the list of features that we can consider dropping, right? So for example, we had the URL. We don't want to keep that. Address, we don't want to keep. Location and listed in city, we in a way derived a feature out of this, so we can drop it. And name of the restaurant alone would not drive the rating. Phone number would not drive the rating. Dish, like, review list, and menu items, we've just seen them above. So we are just dropping these features now, and we will refresh our code after dropping them. So we had 18 features before we dropped them, and now left with 9 features. 9 features we've dropped. Let's check what are these 9 features like. So these are the features that we are left with. So there's a feature called listed in underscore these parentheses type. If you want to simplify the way this name appears, we are saying we'll change it to service type. So this is the category of the restaurant. Let's just use the .rename method, and we can once again have a look at how our data looks like right now. So this is how our data is, and we have all the features appropriately listed. Let's check how many entries are there for this feature called restaurant type, and you'll see this has 87 categories. Now, this is what we tried to do with other features as well. We want to see the value counts and normalize them to see what's the proportion of different categories. Luckily, in this case, if you see, the first 2 categories alone add up to about 56, 57%, which means this would have a dominance of a few categories. While the overall number of categories is about 87, which is a little threatening, if you see, there are only few categories which are critical. Such features can still be used by clubbing the smaller proportion categories into others. That's what we intend to do here. So let's take the restaurant type and do a cumulative sums. Cumulative sum is going to add up all these values as we keep on progressing. So the first value will be 33.58. That's the same. But the second value in the cumulative sum will be this plus this. And so on. For the third value, you'll add this to the previous value. And that's how you'll progress. So we are checking the cumulative sum. This gives us the cumulative sum. And you can see when we finish counting about 5 top categories, we already reached about 73%. Let's take a threshold of 80%. So we'll consider those categories which add up to 80%, let them be there as they are, and combine the less occurring categories into a new category called others. That's what we intend to do. So how we are doing that, we already got the restaurant type cumulative percentage, and we are saying we want to filter for values which are less than the threshold. And we are just checking what are those top category restaurants. So it says these are the top category restaurants. 9 top category restaurants are there, and remaining can be clubbed into others. How do we do that? So we are saying wherever this restaurant type is in the top category, we leave it as is, else we replace it with others. Now, if we check the value counts for the restaurant type columns, you can see it has another category called others. Of course, a lot of categories have been clubbed into one, which is others. We're trying to do some feature engineering with the column called cuisine as well. And of course, cuisine was a little more complex column. Let me just kind of try to show you the output. This has lists within. So for example, this is just one entry which says North Indian. Then you have North Indian and there's a comma and Chinese and so on. There are long lists which are available, right? So we're trying to get 2 pieces of information from this. Whether the restaurant is a core specialty or a multi-specialty restaurant. For example, if you have different types of cuisines, it'll be called a multi-specialty restaurant. And the second is, does the restaurant offer any of the top categories of cuisines? So we'll have to derive this, and that's what we'll see in the next few steps. We are taking the cuisines feature and we are applying a lambda function. It checks if the restaurant is an instance of a string. First of all, it has to be a string entry. And we are splitting the entries within the feature wherever we encounter a comma, because that's how these all are listed. If this is greater than 1, then we call it multi-specialty. You will encounter a comma only in those cases where you encounter more than one type of cuisine. That's where we'll call it a multi-specialty. But if that count is not greater than 1, it's just 1, then we'll call it a core specialty. So we've checked both, that the entry that we're talking about is a string, is an instance of a string, and it has a comma, then multi-specialty, else core specialty. We are just quickly checking. This is a new derive feature. We're calling it cuisine type. We are just checking this cuisine type against the original cuisine feature. And let's see. So we got some matches. So we are checking a random sample of 5 observations after doing this. So we see wherever it had multiple entries, it has been converted into a multi-specialty. When you have just one entry, it would say core specialty. That's a new derive feature. So now we are taking the cuisines column and we are trying to come up with a list of popular cuisines. For that, what we're doing is we are first of all going to ignore anything that's missing there. And then we are saying we would want to split the cuisines wherever we encounter the commas. And then finally, we remove all the extra white spaces. So when you do a dot strip, if you have extra white spaces in the beginning and the end, that those will be taken care of. We'll get the proper entries as the way the text should be. Then we are taking this cuisines list and converting it to a pandas series and checking the top 10 entries. These will be our top 10 type of cuisines. So from this cuisine thing that we've taken, we have combined everything in the cuisines column. This goes through the entire cuisines column and creates a list of all the entries. So for example, you have North Indian and biryani here, and then you have another North Indian and North Indian. So all these will be put into one list. That list is now being converted into a pandas series, and we are checking the value counts. What would this tell us? This would tell us the most popular types of cuisines that are present in this entire column. So let's run this, and you see North Indian is the top choice, then Chinese, and so on, and these are the top 10 choices. Of course, we could have had many more choices, but we are looking at just the top categories. And then what we are trying to see is a particular restaurant offering these top cuisines or not? So this is another level of drill down. So now we are trying to identify if a particular restaurant offers the popular cuisines as we found here. In order to do that, we'll have to go to the cuisines column. So then we are saying for cuisines in the index of the top cuisine counts. What is the index of the top cuisine counts? These names, right? So if a particular cuisine in our data features in the list of top cuisines, as we'll get it from here, we would want to convert it to a yes. Otherwise, we'll call it a no. Right now, we are not counting how many cuisines are there. We are simply saying that if at all the cuisine offered by a restaurant features in the top cuisines, we are making it a yes or no. The alternative way would be to even count how many of the top cuisines exist there. That's another possibility. And then we are just checking how this mapping has come up. Let's just run this. So you see there are a lot of restaurants which have the top cuisines, but this may not always be a yes. When we do this sample, it picks up some random records. There would definitely be records which have no's. So let's just check how many yes and how many no's we got here. So there are about 4,300 odd no's and 37,000 yeses that we got. Now we can drop the cuisines column as well, because that column itself would not be very useful for predictions. It has a list of strings. So we'll drop that. And if you check the missing values in the data now, we don't have any missing value. Now, after this much feature engineering, we start with the usual predictive modeling task. Notice this feature engineering was not mandatory, but it's always recommended that we do, because this encourages us to think a little more from business's perspective. Otherwise, it's a very straightforward exercise that you do certain checks on the data and fit it to a model. So this feature engineering at times could be very, very helpful, could be very insightful.